Okay, I'm going to go ahead and record this lecture. This is going to be this is a replacement lecture for Thursday. I'm going to put a link to it on the e-learning site, and I would like for people to watch this before Tuesday's class if possible, because Tuesday I'm going to go through problems out of the homework. But let me just jump here. Let me just kind of go through some of these, finish up these slides real quick, and then I'll go to the homework where I'm there. I don't like to record this way because sometimes I go a little fast. I'll try to talk slowly here. Right there. Okay, the last thing we talked about right there, this is chapter 3. We're still in chapter 3. Let me just go ahead and go through the slides from the beginning, but I'll go very quickly here. Right there. So again, we're looking at, and I got these turned on, but that's fine. This is, matter of fact, I'm going to end slide. Actually, I don't have let me hook up my keyboard real quick here. Okay. Right there. Transitions, let's turn off the transition set there. There, and then slideshow from current slide. Alright, yeah, transitions are still there. Okay, well, boy, this is kind of a quick review. I know it's been 2 weeks since I met with you. That's why I'm going to go through the time to do the review here real quick. Right there. All right. Right there. We went through the 3 basic gates right there. And we'll see them again here. This is a typical truth table. Let me put my pen on. Right here. Right here. And this is our logic function right here. And we don't know what's in that there. We'll be spending a lot of time on that there. But we've got here 2 inputs and an output. Now this happens to be, if I look at this, this happens to be A naught, B naught, or A B naught equals X is what that is. And I did that by looking at where there's a 1 here. I looked at the 2 inputs here, and I looked at 2 inputs there. And I wrote this in standard sum of products. We'll be using that term quite a bit. And it's very easy to write functions looking at truth tables in sum of products there. And you will probably see at least one part of a final exam question where you'll see something like this here, and you'll be asked to write that function in the sum of products. Again, you would look at, every place is the 1. Now, later on in this hour, we're going to be looking at simplifying this here. Matter of fact, I may come back to this one and see whether we can simplify that there. That there. So, as we traverse through here, we've got the OR function. X is equal to A or B. We got the, and remember OR is that there, but it's not the same. This is the case where you're not sick or having problems. If you write that down, you are just basically using Boolean expressions to set general algebra, Boolean algebra. Either A or B. If in this case A, 1 ORed with 1 is going to be 1, and that's one of the rules we will be looking at later on. That's there. Here, well, we did look at it before the break. There. So again, this is the logic function for it. This is the truth table for a 3 input. And notice that if any of the 3 inputs are high, and the only condition which they're not is right here. Right there. That's the only condition in which they are not. Right. Up there. So again, this is an example. I'm not going to go through that there. And is similar to multiplication, and it's written as A and B and C. In this particular case, right there, if any of the inputs are low, then the output is going to be low. All inputs have to be high. Now, I just said something that's very important when we look at this here, if any input is low, X is equal to is low, right there. Because that we'll be looking at that later on when we write in, as we write, look at NAND gates and NOR gates, alternate ways of drawing them that there. So as we look at this, but this is a typical truth table. Notice that the only place the output is high is when all inputs are high. All inputs must be high for an AND gate. Right there. So as we look at this right here, at the AND gate, there it says we'll only go high when all inputs are high. The OR gate, any input will take it high, right there. Then we look at the inverter or not inverter or the complement. You'll see all three of these terms used quite a bit right there. X is equal to A naught. Normally they say A naught instead of not A. That's just simply the way that most people talk right there. X is equal to the inverse of A or the complement. Those are all three terms that mean the same thing. I realize that English is the second language for everyone here, but in the digital world we tend to use that there. Use it differently. Again, I mentioned this before, this is an alternate way of writing A naught right there, is that we put the little apostrophe after the end of that there. So, and then sometimes if you have the symbol A, B, like that, that means that we're going to not the product, not up there. This is not equal to A not B. These are not the same, and we'll see that here in a little bit right there. This is the inverter. Normally, if you have this bubble that there, some people will use the term nipple. Hopefully nobody takes offense that there, but a lot of the engineers will use the term a nipple or a bubble. For various reasons, the term nipple has become socially unacceptable that there because of its alternate meaning, but you'll still hear it from time to time. So bubble is the correct term right there, or the little circle that there. They say little circle. Normally we refer to that as a bubble right there. The inverter just simply inverts the output. That there. Typical that there. You'll see this circuit quite often actually right there. This is the summarized rules for it right there. In your Boolean expression, 0 order 0 is going to be 0. Again, this is just a repeat of the truth table for 2 input right there. And going back to there, if an expression contains both and or, the and expression must be done first. That's part of our Boolean algebra right there. If we reverse those and put the parentheses, we have to put the parentheses there. That there. So the parentheses changes the circuit a great deal. Whenever you have the inverter, you do the inversion first right there. And note that here, this is what I was talking about. This is the inverted up there. Now, you'll often see, and we'll see that again, they'll just put a bubble on that, and that's called a door gate right there. This is for further examples, and as I mentioned before, I can't repeat this often enough. You will definitely see this problem, not this problem, but a problem like this on the final exam. That's there, where you will have to be given a circuit, and you will be asked to come up with the expression right here, right there. And then quite often that'll be followed up with a follow-up question: is simplify the circuit. That there, and we'll be talking about that in the next week or so, right there. Actually, we'll be talking about that Tuesday when you get back. Here's another example, and as you look at this right here, A or B, and then we write this expression here, then we invert it, then we OR it with the D right here, and then the last one right here is we AND it with the E. And notice that we put a second bracket right here. Otherwise, if we did this first, then it would be expected. So you have to denote anytime multiplication is further on that you have to do that there. Now again, this circuit would most likely be simplified in some form before there. It's a fairly complex circuit there. So rules for evaluating Boolean expression: perform all inversions first, perform all operations with the parentheses, then do the and or the or before the or. If it has the bar, do the inside and then the inversion. Now again, I mentioned that the simplest way earlier is to come up with a truth table, and the truth table, as we'll get further into this chapter, I think it's this chapter, it might be chapter 4, when we start looking at Karnaugh maps, the truth table is critical right there. So it allows you to double check your work right there. Well, we come up with a truth table right there. Now this is a fairly complex way of doing it, but it's actually the cleanest way. It takes time, but notice that we've created some intermediate variables right here, and this is our final result, which is, so if we find out right here, we write u, then this is b is equal to a naught b, and then we find w, which is bc right there, and then we run that through an OR gate. So we go through that step by step right there. This is the first step right there. And notice what we've done, that this is our final truth table that we're going to end up with right there. But as we do this, we do the first row. Once the first row is done, we do the second row, which is B right here, right there. So we come up with it. So we go through this here, and this is A naught B. So so we look at these two right here, A naught B for this one right here. That's one, and A naught B. There's the other one, right there. And then we go through and we do the W, and that's just BC. And again, we're looking at these two inputs. The only place where the two of those are high. And then the last one is we're going to OR these two columns right there. Right there. And we'll see that's high here, here, and here. Right there. And again, we can simplify this by looking at the truth table. Remember, I did the example earlier that I could say that this is A naught B C naught from this row right here. Right there. The next row is OR A naught B C or A B C. Right there. Now, that may or may not be the simplest solution as well. We'll see that later on when we look at Karnaugh maps, but or even applying Boolean algebra. Right there, I can see that I can simplify this a little bit. I may end up actually with the same circuit though if I simplify that there, because I can combine these two, and we'll look at that later in the hour. Right there. And logic can be determined by the circuit noted to the final output. Again, you can go through and you can, oh, my newspaper downloaded that there. This is the same type of thing where you go through and you input A, B, C, and D, and then you write the, this is your T output, this is T, this is U, this is B, and this is X right there. Going back to our, right there. Sometimes a technician will go through and you will input A, B, C, and D to come up with this truth table right there. Again, this gives us our intermediate values. Sometimes we're not interested in our intermediate values, because as I go through and look at this right here, the only place this output is a 1 that's right there. So I could reduce this to a single gate very, very easily there, because as I look at the final output, X is going to be equal to, and right there, A naught B C D naught right there, to a single input right there, or single output right there. So a lot of times our circuits are much more complicated than they need to be, especially in this part of the book. Nope, going in the wrong space bar. Okay, it's also important, again, this is going to follow up on the final exam, that you be able to draw a circuit from the truth table, right there. This happens to be a sum of products, right there. We require 3 AND gates with 2 inverters. 2 of the inputs are inverted, right there. So we also require 3 input OR gate, and we're going to end up with a circuit that will look like this here. Again, you're given this expression, you need to come up with this circuit right there. So, and there's plenty of problems in the back of the chapter. We'll look at the textbook here later on. Out there, again, this textbook I did post on the e-learning site out there. So again, this is another example right here, and right there. I don't know what my other computer is doing, but right there. So again, we're looking at this is A and B, or and B. This is B naught and with ORed with that there, and then this is my final answer. This is written in a product of sum notation, where we're taking this is a sum, and we're multiplying them all together at the end. That there, those are our 2 standard forms of outputs. We'll be looking at those in far more detail later on. So that there, again, we're looking at outputs of NANDs or NORs. And inverting it, again, those are our 2 other gates right there. These are our NOR gate right there, and all it is an inversion of the OR gate there, and then I'm not going to go through that there, and this is the NAND gate right there. So those are all of our basic gates there that we have there. It's quite funny, the professor that I had for basic digital when I took it many years ago, his name was Professor Gates, Harry Gates. Right there, very nice guy, man there. But he was the person that I had for my basic digital course. Although I taught computer programming with the name Hack, so some people probably will talk about that later on. Again, when we put the NOR gate there, here is a circuit here. And whenever you see this bar across the whole multiplication right here, so we got 3 inputs, A, B, and then C and D naught, that is going to input a 3-input NOR gate or NAND gate. And here we've got, in addition, with the bar across, that's going to denote the NOR gate right there. So again, these circuits are getting a little bit more complicated. Now we're going to get into the basic theorems. This is what we covered last before we went on the break. That's there. So our basic theorems as we go through there. The first is anything ANDed with a 0 is going to end up being a 0 right there. Remember when we look at an AND gate that if we have anything being a 0, then the output is going to be low. So this will also hold, and this may disappear, if I have 5 and one of these is a 0, the output's always going to be a 0 right there. And if we input something with an AND gate, let me erase my marks here, right there. If we have a 1 then we could basically ignore that input there. Now sometimes we'll use this theorem in a case where we've only got 4 input AND gates and we only need a 3 input AND gate, so we will just tie one of the inputs to a 1 to get around that problem right there. And again, here we're saying anything ANDed with itself is equal to itself right there. So again, they're saying we can go through a truth table and see that that is true. This is another way of getting around the problem. Sometimes we will do this, as I mentioned in class, where we have a problem with a buffer right there. Now, this is an interesting thing here, that X ANDed with X naught is equals 0. Now this is a very interesting circuit because this is sometimes used to create a short clock edge detector. And let me kind of just show what I mean by that. Up there. Oh, wrong pen here. Just add a page. I just keep adding the stocking, keeps getting larger. If I take this circuit right here, and I put one input in here, and I take and I put an inverter here, and I do this here, we have to keep in mind that if we put a 1 on here, it goes to a 1 right here. This output also goes to a 0 right there. But when we look at the timing pattern, this is going to go to a 1 here, and then this is going to go to a 0 here, and there's a delay right here, a delay right there. And depending on the technology you're using, this delay can be 5 nanoseconds, 20 nanoseconds. It just depends on what type of technology we have here. Right there. For this short period, this output is going to go high right there. Because we're assuming that this is a low already, it goes to a high. So this goes high. This goes high after so many nanoseconds. So this output will go high and then it will go low, and this is a very short period that it's on. And this is used to detect an edge for clock signals later on. So this circuit is used for a number of applications right there. Right there. So we talk about that there, and I'm going to pause this, and the reason I'm going to pause this is my sinuses are plugged up. Yeah, actually, I guess I need to give me a second here, pause. Okay, sorry about my little delay there, but I don't think you wanted to up there. So okay, but now that was just kind of a side note, that discussion regarding this being a pulse detector. For right now, do not worry about that. I'm just kind of pointing out that this circuit, even though we say that the output's always going to be 0, is used from time to time. Right there, it's a very common way of detecting a pulse edge. There, you know, and it has actually created problems in some cases there. Now, as we move to our other theorems, we end up with anything x plus 0 is going to be equal to x, right there. Anything x plus 1, the output is always going to be 1, that there. And again, that goes back to an OR gate, and we can extend this to many. If we have 10 inputs, the output is always going to be 1, right there. X OR with itself is going to be 1. X 1 plus 1 is 1. 0 plus 0 is 0. And again, we also have this situation where x plus x0 is going to be 1. And again, this circuit can also be used for detecting a negative going pulse right there. You know, similar to what we have that there. When this goes to 0, it takes some time before this one goes to 1. So we have a very short period where the output is going to be low right there. Up there. And it depends on what technology you're using. It can be into the 4 or 5 nanoseconds all the way up to a millisecond with very old technology. Right there. All right, now we're getting into our multivariate, commutative, and that there is simply matter is connection. Again, we went through these before, but review. Associative laws. Again, that basically says it doesn't matter which order. Now, these do have meanings in circuits right here, and that what this says is that I've got 2 OR gates right here, right there, right there, and this is A, B, C, and this is X right there, or I guess this is X, Y, Z right there. It doesn't matter whether I flip these around and change which ones I hook up right there. So I can hook it up X, Y, Z, or I can reverse these and put Z here and put X here, and the output's going to be the same right there. Or I can do a single 3 input. I guess I'm using AND gates here instead of, I'm actually doing 12, but I can do a 3 input, and all 3 give me the same result right there. Now the distributive law is one that we'll use quite frequently, and what this says is that I have an OR gate right here, Y and Z, and then I'm going to run it through a AND gate with X here, and that's the same as if I have 2 AND gates in an OR gate right there. And this is X, I'm going to put Y here, and then X here, and Z here, right there. And this is the same type of thing here where we're doing, and we'll be using these laws here to simplify our circuits. And let me, I picked a bad time to be doing this because okay, and so now we get into our multivariate here. This one's a little bit trickier. This is one I never remember, to be honest with you, and so as I'm solving problems, I tend to forget about this one. But first one here is fairly easy. 14 is fairly easy, and you can solve that by saying X ORed with 1 plus Y is going to, this term is always going to be equal to 1, so it just equals X. These two are a little trickier, and that is X plus X naught Y is equal to X plus Y, and X naught plus XY is equal to X naught plus Y. Those two I tend to forget right there. So there's a table for showing that there. This is actually doing the first one right there. That's right there. The second one is shown later. I'm not too worried about that there. That's the table that there. About necessarily using those, because later on we're going to get around. De Morgan's theorem is a very important one. It's a very confusing one up there. Right there. This one is very important, and we'll use this one a lot out there in some of our development of our further theory. But this is X or Y not, or X nor Y is equal to not X ANDed with not Y right there. And then the inverse of that is X NAND with Y is equal to X not or Y not right there. We use those quite a bit. Now this also leads to another way of drawing this, and this is saying that X Y right there is equal to or XY right there. So the same thing here, this is saying that or XY. We'll see these alternate gates drawn later on here in these slides that there. Matter of fact, right here we see them that there. So you'll see that right there, an alternate form. These really haven't caught on, but they do exist there. Again, this is the same thing right there as we're looking at here. So NAND gate can be used to create 3 basic functions: the OR and an invert. Very flexible. We come up with here that we can say that by tying 2 inputs together, we got the NOT. By tying two inputs, we got the NOT, so this is equal to an AND gate, and this is equal to our OR gate by using our De Morgan's theorem here. And these are our two inverters right there. So what this is saying by doing this is it's possible to implement any logic function using only NAND gates and no other type of function out there. So a NAND gate is a universal gate. It can be used to do anything. And again, we can come up with the same rule of thumb with the NOR gate. These are universal gates. You can do anything you want with them. We'll look at, as I go through some of the lab demonstrations, I'll be using a technology called field programmable gate arrays. That's there. And these are basically a device that allows us to implement any circuit without having AND gates or OR gates separate, that they're built into the combination right there. So, as we look at this right here, a logic circuit is generated an XO will exist something up there. We have the expression right here. These are the chips that we typically use. These are 74XX family. 74 LS means low powered, high speed. That's there. The LS is the family, and the 00 is the functionality. So this is a 74XX LX family. 74 means it's basic logic. You'll sometimes see 54, which is CMOS, which is a little bit different. 74 replies to transistor logic, or TTL. Up there. This is a 4-input NAND gate, or a quad NAND gate. We'll use it's a quad NAND gate. I don't forget the word. I said 4 input. It has 4 NAND gates on the chip. This is a 4-input or a quad 2-input OR gate. There's 4 there, and this is a quad 2-input AND gate circuit. So we've got 4 chips on each one of these. And these are pretty much, if you have a quad 2-input, they pretty much use this type of wiring pattern right there. So again, typically what we would see if we were going to build this is that we would have 2 AND gates used and a OR gate. We would require 2 ICs to build this. Now they show this here, right here. These 2 AND gates are on one chip, so we're using pins 1 and 2. So this is we're using this one for here. We're using 4 and 5, this one for here, right here. And then over here we're using 1 and 2, so we're using this chip right here. So this is the way we would wire this up. We would tie this to 5 volts. I realize that this class does not have a lab, which I consider a problem, but we will see this implemented in a FPGA, our circuit set there. So, but this is the way we would wire this up right there. We can also wire this up using our NAND gate implementation right there. This does not show the NAND gate configuration, but you would have to go through and apply the NAND gate rules to that there, and we would then implement this with only one IC right there. And that's the advantage of only using a NAND gate. It didn't reduce the number of gates in particular, but it reduced the number of ICs, and in particular it reduced the types of ICs. As you notice that this part number is 74LS00. That should lead you to the understanding that 00 means that this is the first component in the system, in the family. This is the most important one. So when you do implementation out there, a lot of the engineers try to use just the 00 and nothing else, because that reduced the inventory in a factory that you had to have. It reduced the number of spare parts you had to have. You didn't have to have 15 different types of ICs. You didn't have to carry AND gates, OR gates, inverters out there. You only had to carry one, just the 7400. right there. This is just showing the converted standard symbol to alternate. We won't be using this right here. I'm going to just kind of skip that there. All right, points there. None of the symbols have bubbles, so all the alternates do, and we're not going to discuss that right there. Active high, active low. Now these here, active high and active right there, this is important right there. This is an important discussion, is whenever we use an active high, input or output has no inversion bubble if we're using active low. What we mean by active is if we have a signal that is going to do something, or if the input is valid, we can either use an active high or an active low. Active high means that 1 means 5 volts or 3 volts, depending on our technology, or active low means that 1 is ground. Now, quite often we will use active low for both input and output for 2 reasons. One is that if we look at the circuitry, and I'm probably going to have to erase this, but if we look at our circuitry right here, we put this right here. This is our output, and let's just show an LED. This is 5 volts, and let's just show an LED with a resistor right here. Right here, this is an LED. If this output is low, 0 volts, then this is going to draw a current through the transistor, but this has no power drop across, voltage drop across this. This is a closed switch in the TTL world. Our transistors are either turned all the way on or all the way off, so we dissipate no power. If we go the other way and we're going to have this be our output, then when we draw a current, we have a voltage drop across here, and thus we're dissipating power and heat. So if we have any kind of current draw, it's better to use active low, because we're using what's called an open drain output or open collector output. Quite often you'll hear the term open drain because you're talking CMOS. Up there, here we're talking TTL, so it's open collector. Up there, where we supply the ground. So if we want the LED to be on, the motor to spin, or whatever, we will use an active low right there. Active high means that we supply the current right there. Other cases here is that right here, this is our input, and this is our push button right here. This is going to float high whenever that's there, and when I close the switch, that supplies the ground. So when I push the button, the input goes low. That's there. So that tends to be a little bit better than the other option here of if we put and I'm going to show this here and show the push button. I push the button to open the circuit to take it high, because I've always got current going through this circuit right here. So typically active low is the preferred method. That's there. So active high, active low. So this, quite often you'll see these little bubbles right there. And we'll see this more and more. You'll see this more often when you get into microprocessors right there. Now, again, I'm not going to get into the alternate gate symbols that's there. But if we look at this right here, this is actually a NAND gate right there. That there. Excuse me, that there. Right there. So it's another way of writing the NAND gate there. This is actually a NAND gate that there. Typically, this doesn't matter, so I'm not going to get into that there. So there. Now, you'll see this quite often when you move into microprocessors. This is what I was talking about. This is a read not line. This is a read line right there. So high or low state there. So we put the bar over there. It means it's active low. So that means that when that line is low, that microprocessor is in the read state. Now some lines will have something that looks like this. This is a read/write not line right there. When the signal is high, it's in a read operation. When it's low, it's in a write operation. You'll see these quite often in microprocessors. Right there. When possible, use so bubble connections are connected to the bubble input. I'm not going to right there. I'm going to skip through this right here. All right, we talked a little bit about propagation delay right there, and that's the amount of time it takes at there. And parts sheet states the propagation delay. This determines when the time it takes for an input signal before the output goes valid. This is the propagation delay, and these can create headaches for us down the road. So we'll be looking at that there. Now, I'm going to change the subject quite drastically, and then I'm going to probably wrap this up here. Is hardware description languages that they allow us to. These are languages that look like programming languages, but they represent logic signals right there. Now, the author who wrote this book, he learned this part of the book. Greg Moss, I worked with him for a while. You know, we spent a couple of months off and on working together at the Microelectronics Center. I continued to work there, but at there he did not do much design work there, but he learned HDL about the same time I did. This was back in the late 80s, I think it might have been, or early 90s. Early 90s. There's a company called Altera. Altera makes a family of complex programmable logic devices right there, and they developed a language called Altera Hardware Description Language. Out there, it's not a universal language. It's just for describing circuits for Altera. Altera was just recently bought by Intel. I mean, they're a big company. I visited them back when they first opened up. Matter of fact, I met one of the founders way back then and was implementing Altera in my courses. That's probably my major area right there. And they developed this language called AHDL. AHDL is a very good language for learning programmable description language, hardware description languages. It is not implemented anymore. It's not there. So we'll look at some of the examples, but AHDL has gone by the wayside. Altera quit supporting it in their software, which is a real regret. I loved using it in my courses. It was replaced by a language called VHDL, which is a very high-speed integrated circuit description language. This language was developed by the U.S. Department of Defense. They didn't actually write it, but they contracted with a number of vendors to develop this language. They paid for it. It is the standard language in the U.S. and parts of Europe. It is not used very often here in Asia, but I will use it in my discussion here because that's the one that I've been using. There's another hardware description language that's not talked about in this book, and that is called Verilog. That is the more common language you will find. There are very similar languages, but I will use the VHDL discussion. We're not going to learn a lot of VHDL, but we will look at there. This is another way of designing circuits, right there. Right there. So, important to distinguish between hardware description language and programming languages. In both a language is used to program a device. However, when we look at programming languages, things are done in a sequential order out there, and they execute one instruction at a time. When we're looking at VHDL, things are typically done simultaneously or concurrently right there. So we have this concurrent monitoring all inputs and responding to any changes. So we can have multiple things occurring at the same time. And digital circuits, there's programmable or hardware description languages usually equate down to hardware. right there, where a software or programming language, the hardware doesn't change right there. So comparing the two of those, we can look at a right here, y is equal to, go back to this right here, the output y will be high within about 10 nanoseconds. In other words, that's the propagation delay, point that both A and B are up there. If we look at a programming language, we have to go through and we have to look at each input individually and make a decision right there. So it's a series of steps. So in most cases, using a hardware description language and going to hardware is going to end up with a faster circuit, but it's less flexible once it's been built right there. Programmable logic devices can be programmed, and we'll be looking at some of those. Matter of fact, I'll probably bring one to class on Tuesday to give a short little demonstration right there, right here. This is a PLD. Again, what we're looking at here is we've got, looks like about 9 inputs right there, and they can be AND together right there. You want to set up a programming connection right there. Hardware language. Hardware language makes programming PLDs much easier trying to draw that there. Most digital design is using logic circuit or using hardware description languages today. Right there. I'm going to kind of wind up here at this point. I'll give a short little demonstration here, but this is a very simple AND gate, and we've got the format up there. Again, this is not a course in HDL. Actually, when I taught this course back in the U.S., we skipped this part of it, and we had a separate course on just HDL programming. Since you don't have a separate course in HDL programming, I'm going to spend some time on this here. So basically, we look at here, this is the AHDL. Let me skip the HDL and just go straight to the VHDL. Right there, VHDL looks like this right here. We have 2 parts. One is we're describing the fact that we have a black box. This black box has got 3 ports, A, B. A and B are inputs, Y is our output. Now I should note that I don't use X as an input or output because X and VHDL means don't care. So X is a keyword. You cannot use X right there. But X and A and B are inputs, Y is an output. This is the first part of it. Then we define the functionality of it and the architecture of our circuit. This is just an AND gate is. You make up this name here, AND gate has to match this. These two have to match. NNT AND gate and AND gate. Just like architecture circuit and end circuit right here is, and Y is going to be equal to, put on to Y the result of A and B right there. So this is a very simple VHDL program or design that implements an AND gate right there. So every entry must have at least one architecture associated with. In advanced programming, we may have multiple entities depending on the number of inputs. I mean, it could get quite complex. We're not going to get nearly that there. We have the body, which has within a begin and an end, and inside there you describe what the functionality of the device is. So what we have is the top part here says we have a black box with A and B, and Y comes out. The bottom part tells us that inside this is an AND gate right there. So we have 2 parts of every design right there. So again, we can have buried nodes that are not seen inside. Again, this right there. And what this simply says here is that M is buried within there. So we say that M is equal to A and B, and then Y is equal to M or C. and this here just simply says it's an intermediate signal. And with that said, I probably have covered more of that than I really intended to. I want to go back on Tuesday and go back to our Boolean expressions right there. So let me stop this here, and it's fairly short, 15 minutes.